Okay, welcome. So today we're going to introduce a new topic, and this topic is purely for informational purposes only. It's not going to be on the test, obviously, or the final exam, I should say, because we'll only have one class to discuss it. And the other thing is that it really doesn't give you enough time to sort of do any practice problems or anything like that. But I think it's a really good topic. It's not one that I've frequently seen in control systems analysis. There are some systems that have sinusoidal inputs. One of the things I can think of is if you're on a diesel generator, and one of the things that's really important to know is the speed of operation. And one of the things that they do is they have a little, almost like a proximity sensor, but it uses magnetics. And so as the teeth and the sprocket go by, it creates a little pulse because the sprocket's made of some sort of ferrous material. And you have this little sensor that just has a magnet associated with it, and it detects the change in how much magnetic field is occurring, and then that's just a little pulse. And so you keep pulsing, and then because it's magnetic, you have that kind of smooth curve. So you end up getting essentially a positive sine wave. I don't think you get the negative sine wave. I've actually never seen it, but at least you'll get the positive sine wave. And so you can convert that to a frequency, and then you can do frequency response that way. So the other reason why I really like this topic is most of you all, if you remember from John Allen's class, I believe it's 342, maybe perhaps 241, but you actually do frequency response and you look at break frequencies and you might maybe actually do Bode plots. And one of the things that John does, he does a great job of explaining, okay, here's the break frequency and then doing the analysis. Well, there's a lot of math that actually goes into that. And if you can do it with Laplace, it dramatically simplifies the math. And so what we're going to do today, excuse me, what we're going to do today is we're going to develop the approach, at least the approach of how we can do Bode plot analysis by using that really powerful variable that we love so much, the Laplace variable S. Okay. So a little bit of background on it, and we'll just briefly talk about root locus. Again, we're looking at the transient response of a control system. That's why we look at the poles and how they move to zeros. And then what we're looking for is essentially the steady state operation. And if you recall, we looked at settling time as an important characteristic. We also looked at percent overshoot. Those are transients that will decay with respect to time. It also has to have a pretty precise model representation. Whereas the frequency response, it isn't looking at anything from a transient's perspective. It's looking things over sort of over a certain time horizon. So it's not really looking at things respect to hey, here's my percentage overshoot. It's looking for more things like how is the system going to respond over like the period of time. So that's why it's the steady state performance. So they're complementary to each other. So the root locus, if you can actually do a root locus, gives you the transient response, whereas the frequency response tells you what the steady state output is going to look like. That's why they're complementary. All right, so let's look at a system, any old transfer function. And we're just going to represent our closed loop transfer function. So if you want to subscript this with a closed loop, you can see that that is our closed loop representation of any old system. And we know, or we've been looking at this entire semester, we've been developing transfer functions that are a function of the Laplace variable S. But if you recall, and this has been a while since we looked at it, we did introduce the Laplace variable as the complex representation of frequency. So what we can do is we can substitute S equal to j omega to go ahead and do that. And if you can't remember, let's look at a simple circuit. Here's a resistor capacitor circuit, and this is modeled in the time domain. And what we've been doing this semester extensively is how do we do block diagrams? How do we do transfer functions, yada, 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 to go ahead and bring that into the Laplace domain. Well, is there another maybe more useful, at least for some of us in this in EET, that perhaps is maybe another more useful way to do some circuit analysis on this particular circuit? Do you all remember? Or can you think of one that actually is relevant to what probably most of you are taking this semester for courses with me, and you can analyze the circuit? You can say no, it's not obvious, but. Well, we can't remember. What happens if we restrict the input to purely sinusoidal input? No DC, no ramp, no parabolic, all going to be sinusoidal inputs. Is there a way that we can represent the circuit to analyze it that we're pretty comfortable with? How about, so this V in of t is going to be equal to some voltage sine of omega t. Now, we can analyze the circuit using differential equations to solve it, or what we can do is convert this circuit to something that may be familiar to you, hopefully it's familiar to you, where this is V divided by the square root of 2 at an angle of 0, and this is negative J x sub c. So this is AC circuit analysis, correct? So we're doing AC circuit analysis, and we see that we can get very similar results. In particular, if we take this to the Laplace domain, this is R, this is 1 over CS, this is V out of S, this is V in of S. And what we see is if we substitute J omega for S, so S equals J omega, we end up pretty much with that particular circuit over there, where we have the R and the negative J x sub C. We also have a little bit, so this is a little bit more of a stretch in terms of how our V in of S becomes just an RMS quantity at a specific angle. But the reason why we do that is it's a simplification, and we're trying to get correct power calculations. So it's not a perfect analogy of how to go from Laplace to our phasor representation, or our complex frequency representation, or steady state representation, but it does a pretty good job. But what we see is the capacitor is negative J over x sub c. And maybe what I should say is x sub c is 1 over 2 pi fc, which is equal to 1 over omega c. And if I plug in the value over here, I have 1, let's do it over here. This is 1 over j omega c, which these look pretty close to each other, right? But remember, a j in the denominator means negative j over omega sub c. So those are exactly the same. So we actually have been doing for quite a while, going all the way back to your AC circuit analysis, we have been doing for a lengthy period of time, where we've been converting the Laplace domain circuit into complex frequency representation. And we can go ahead and extend that to go ahead and do Bode plots, because Bode plots, the difference about doing AC steady state circuit analysis is because we're using one frequency. Typically in North America, it's 60 hertz. Whereas when we're doing Bode plot analysis, we are allowing the frequency to change pretty much anywhere we want it to be. And including, we can also do a really basic one in DC. So what we have now is we've just got to do a little bit of work and analyze the system so that our frequency can change. But the approach is still the same. So we can see that I have a G of J omega, which is the amplitude or magnitude, and then I have an angle associated with that, just like what we did when we wrote our phasor over here. But now this is our phasor, because our G is our electrical system or our mechanical system, and that's represented as an impedance. So what we can represent is this has a magnitude of Z and an angle of theta Z, just like we do when we see over here. So we have negative J omega x sub C. Well, that's equal to x sub C at an angle of minus 90 degrees. So in our circuit, we can go ahead and just look at our capacitor specifically, and we can see that we have an impedance and an angle. And that's the similarity between the two. So remember, in your calculator, you probably have the angle symbol. In MATLAB, we have to use Euler's identity. So we'll just go ahead and use those interchangeably. All right, so let me erase some of the stuff so we can see what we're working on. Too fast. Okay. So here is our block diagram. And we have an input, a voltage, or any signal, right? Doesn't have to be a voltage. And then we run it through our system transfer function. And then we have a corresponding output. So that's our magnitude, that's our phase. We talked about that. For the case of a sinusoidal input, we have it arbitrary, right? So we have any amplitude sine of any specific frequency. We'll call it omega sub 1, but it doesn't necessarily matter. And then once we achieve steady state, and in this case, we say 4 time constants, but it can be, 5, it can be 3. It just depends on which one you're using. Some people say 7, but let's just say 4 for this case. So after 4 time constants, then what we see is our steady state output becomes the amplitude times the g of j omega. And then the sine, it's going to have its original frequency in here, which makes sense because when we run a 60 hertz signal through an AC circuit, we can get voltage drops and currents, but on the output, we're still going to have a 60 hertz signal, but we're also going to get a phase shift. And that phase shift is specific to the frequency that we're looking at. It's not at a it's not a fixed phase shift. It's always going to, or perhaps could vary. And that depends because in my RC circuit, my X sub C value or negative J X sub C looks very different at low frequencies than it does at high frequencies. So our linear time invariant system, a sinusoidal input, better mean we have a sinusoidal output. And we talked about the same frequencies, and it has a magnitude scaling, and we may have a phase shift. Again, it depends on how the system is configured. So looking at this circuit, can anybody tell me here, just thinking about it kind of randomly, if I look at the circuit, do I know if it's a high pass or a low pass filter? Let's just look at that quickly. Is this a high pass or a low pass? Or do you not know? Anybody want to guess? How would you analyze if it's high pass or low pass? What's the analysis technique that you were taught? I'm assuming maybe in did John cover frequency response in 312 or 111, or that would have been Jude. Does anybody know? Were you exposed to frequency response in 312 or 342 or 111? Anybody?
I do remember going over it at some point.
Did you do it with simple components like this, RC circuits, or did you have transistors and such?
Yeah, it was RC circuits, and I think we may have gone to transistors later.
Okay. So with that being said, how were you presented the idea if this is a low pass or a high pass filter? How did you know, or how could you determine which one what it was?
Is it where the resistor is?
Say that again.
Is it where the resistor is what determines it?
It's usually more where the capacitor is, but maybe it's saying the same thing because if we swap the capacitor and the resistor, obviously if we swap the capacitor position, the resistor position has to change. But generally speaking, it's where the capacitor, at least from my perspective, is. And the reason why that's the case is I simply do this. I say this is R, and this is negative J all over 1 over omega C, right? That's where we substitute our impedance term. And so then I start to think about it. Okay, so let's do a table. So here's omega. And here is 1 over omega C. So this is essentially the magnitude. And then what I try to do is I'll try to draw or kind of come up with an angle of what this negative J term becomes. All right, so let's start off with the easy one. How about an omega equal to 0? Can you have an omega equal to 0 in a system? Kind of odd, right? If there's no frequency, then do you really have omega? You don't really have omega, but you do have a DC input. right? So what's 1 over 0 equal to? Infinity, isn't it? And what I see is this minus j over omega sub c term I have over here. That's always going to be equal to minus 90 degrees. Now, let's go to our omega. Our omega term is going to be equal to essentially equivalent to what that capacitor is. So 1 over omega, which is 1 over c times c, is equal to 1. And then this is still going to be minus 90. Now I'm going to go to do 10 over c, just to kind of make it easy calculations. And then I see that this is equal to 10, or 1 over 10, I should say. Let's just do one more. Let's do 100c over c, I should say. And this is equal to 1 over, whoops, equal sign, 1 over 100. So if I look at this circuit, right, what I'm seeing is here's my resistor. That's fixed. That's never changing. But what I see with my capacitor is that DC, this value is equal to infinity. So how much current goes through the capacitor when omega is equal to 0? How much current goes through here?
Yeah, I guess 0 amps will go through the capacitor, everything else will go through the resistor circuit.
Right, so all the current goes through here, right? If any, for the load. So essentially, if this load here, if the load over here is pretty high, the voltage drop is going to be equal to 0, right? So what I have is my V input becomes my V out at DC, right? They're the same. Now move over to here, where I have equivalent to a 1 ohm resistor. So here's my V in, and my V out is going to be equal to 1 over 1 plus R times V in. Let's do another one. R plus minus. This is equal to 1/10 or 0.1. So here's my V in, here's my V out. So I have 1 over, or sorry, 0.1 over 0.1 plus R times V in. What happens here? Any thoughts? We can basically say that if R is much, much greater than 0.1, then V out is going to be equal to 1 over R times V in, or approach that. And so what ends up happening is, what I'm seeing is I'm actually dropping the voltage as I go through the system. So what type of a system is this? This is a low pass filter, because all of the input gets passed to the output under DC conditions or low frequencies. And as I increase my frequency, I get less and less and less of my V out, of my V in and my V out. So that's a low pass filter. That's how you analyze these. Usually what I do, so I did a lot of frequencies here. Normally what I'll do is I'll do a low frequency, I'll do 0, and then I'll do a high frequency, infinity. Because once I see that I have infinity, I truly will get to that value of essentially a very small value, right? I get essentially all of, none of my output will be there. It basically will have all my current will go through this one. And so it drops all of the voltage. And so I have no output. So that's how you can quickly look at these circuits and figure out if it's a low pass filter, or if it's a high pass filter. And these are pretty simple, right? This is just an RC circuit. And you can move the capacitor position. So as Howard pointed out accurately, the location of the capacitor and resistor changes from a low pass filter to a high pass filter. So just for fun, if you want to do a little practice, try doing this one just by using, sort of general analysis, and see if you get the fact that this is a high pass filter. By the way, can you do this work with inductors? Can you substitute inductors for capacitors? Anybody? Is that a trick is it a trick question? It's not intended to be.
Yes, you can.
Absolutely, Giannis. Thank you. Yeah,
You can even have both, right?
you can use both. Yeah, you can substitute inductors for capacitors, and it does change the low pass and high pass, so you do have to switch them around. But the reason why we oftentimes don't see inductors and capacitors is if you've done any, circuit design, there are millions and millions of different versions of capacitors available for you. For inductors, you can buy some, but they are far more limited in terms of their availability, because most of the time you just design it yourself, and they're pretty easy to build. An inductor, you just take some sort of a ring, a piece of metal that's wrapped in a ring, and usually, hopefully, well, I don't know if you want it to be with any currents, but usually you can just take a piece of iron, wrap some wire around it, and the number of turns will help you determine what the inductor size is going to be. So the reason why you can, but you don't see a lot of RL filters is because you just don't have the availability of hand or already built inductors as you do capacitors. You can do them, and then when you see in higher power applications, like when you look at variable frequency drives, you sometimes will see inductors, inline inductors. They're called reactors once they get to decent power applications, where you actually put them in line with your circuit. And then what that does is that provides a low pass filter. So allows a 60 hertz stuff to go through, but nothing else. And so you'll see those at higher power applications where capacitors really don't have the same benefit, and they can cause some other problems, but they would work perfectly fine. So let me erase some of this stuff because I've been writing all over my stuff here. Whoops, isn't this erasing? I'm going too fast when I do it that way. This computer seems to be slowing down. Okay, so here is converting to the Laplace domain, and if I erased it, but remember, if I want to convert this to the Laplace domain, I can do my circuit substitution, and then I have 1 over CS. So when I do my block diagram, or my transfer function for this, where I'm trying to calculate output voltage as a function of input voltage, all I need to do is E out equals E in times 1 over SC times R plus 1 over SC. So it's just voltage divider, right? It's just a voltage divider circuit. And so I do a little bit of simple math and reconfigure it, and now I get 1 over tau S plus 1, right? So this ultimately is equal to 1 over S plus 1 over tau. But you get the idea that we can get our time constant from that. So I have a pole, if I notice here, I have a pole at, let me erase this so that you can see that. I have a single pole at -1 over tau, which is a good thing because we know that we should have e to the minus t over tau for a simple first order RC circuit. So I have that single pole at that value. Now I'm going to go ahead and substitute my term j omega. So this is the huge difference between all the control system stuff that we've done and Bode plots. And it's very different, but there's a reason why we'll do it. And hopefully it will make sense when we start to look at break frequencies and how to calculate those. Remember how what we did in Laplace is we always wanted the highest order S term to be multiplied by 1. And the reason why we want that, so up here a little bit. And the reason why we want that is because when we look at the Laplace table, this is always a 1 that multiplies over here. In Bode plots, we do not want the 1 there. Where we want the 1 is the term that's not associated with S. So when you do Bode plot analysis, these are how you want them configured, okay? So apologies for how things change, but we have to shift our thinking because now instead of getting this 1 S plus 1 or S plus tau or whatever you want to say, now we have to do 1 plus S times tau, just a different representation. And now we can see a little bit of why we might perhaps want to start configuring it this way. Because when we calculate our magnitude and angle, remember, we're trying to look at magnitude and angle plots. That's what a Bode plot is. The Bode plot has two parts to it. It has a magnitude plot as the frequency varies, and it also has a phase shift plot as the magnitude changes. And I'm not sure if you realized that when you were doing Bode plot analysis with John, but you do have that phase shifting component as a result of that. So what we can see is when we represent it with a 1 over here, well, we have a 1 squared, which is 1. But then we also have this term over here, r times c squared times omega squared. Now start to think a little bit about that, because that might help us understand what the break frequency is. And then our inverse tangent. So what we have is we have an impedance plane, or we have an S term over here. So this is the imaginary part. This is the real part. So vectorially, what we have is we have 1 and we have r c omega in our right triangle. So you can see when I'm calculating the magnitude, I have this term here. And then if I want to get this phase shift here, that's just the inverse tangent of the opposite, RCW, over the adjacent, which is in this case 1. So that's how that term is developed. So let me erase this a little bit. Give us some room here. All right, so let's let RC, the combination of the two, so whatever resistor capacitor combination you did equals 1, to simplify the math a little bit. And so now all we have is 1 over 1, the square root of 1 plus omega squared. And I have a tangent, inverse tangent of omega. And again, we're going to see why making this assumption about RC equal 1, at least for this first pass, it makes it easy to follow. So just the Euler's identity representation of it by doing magnitude and angle. And sorry, I know I did this already for you, but what you can see is if I draw this, on an axis, great, you can see the real part, the imaginary part, the 1 and the j omega, and then the 1 plus the j omega term. And I'm actually showing it here as this is showing the actual pole position. So this really would be what our pole 0 map would be. So this is the S plane for pole 0. So here's our, if we do this in MATLAB, and it's really easy to do in MATLAB. Anybody have an idea of how to do this in MATLAB, or do you want to see it done in MATLAB? It's a pretty easy plot to do. You can actually do it by hand. Does anybody want to see how to write this in MATLAB, or just you're satisfied with just seeing magnitude and gain response? I'm not hearing any people, so we probably don't want the MATLAB, which is fine. But what we see is at low frequency, look at the magnitude. So the magnitude of G starts at 1, and then it goes lower. And then our frequency at DC is 0, and then it gets all the way to, this shows minus 80 degrees. And so what this shows, again, is that low pass filter capability, because what we're seeing is we're getting all the output of our system, right? Because our transfer function tells us this is what our value is going to be. It's going to be equal to 1 over tau, S plus 1 over tau. So it's our voltage divider scheme. And so we're getting all of the input. So this is why the magnitude is equal to 1. All of the output is going to be equal to the input. As our frequency increases, it goes down and down and down and down. And this only shows you 5 radians per second. If we went up to 50 or 500 or even more, what we'd see is this would continue to trend to, if you had an infinite frequency, it would get to 0. It's the same thing with our phase shift. Our phase shift at DC, there is no phase shift because there's no current going through our capacitor. However, once we start getting some current there, now we're going to get a phase shift between the two. And so our output is going to tend to a negative phase shift. And we know over time that this should approach minus 90 degrees. Okay. And you can see it starts at 0 and it works its way down, 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 and down. And the only reason why it's not at minus 90 is because we have some resistance here. And when you think about it, as this value of resistance is fixed, and then our capacitor value is fixed, but our frequency is increasing, that becomes more dominant. Our X sub C value, because our X sub C is 1 over omega C, as I increase the frequency, so this goes up, this goes down, which means this impedance drops, so I have more current going through here as I continue to go on. And as I continue to increase it, the resistor value looks less and less important because my capacitor, because it's so small, is allowing all that current to go through there. And then I see the full 90-degree phase shift across that resistor. All right, so why do we plot in Bode plots? Why do we plot in logarithmic scale? Well, it actually is just the purpose of doing logarithmic scale is it just makes the math way easier. That's only reason why we do it. It's not that we're trying to get cute with something. We're trying to display more information, which is typically when you would use log paper or semi-log paper, because this is actually going to be, it's actually going to be semi-log paper because, is this semi-log paper? Let me think about that for a second. Yes, it's semi-logarithmic paper because the x-axis is logarithmic and the y-axis is going to be the standard value. So what we do is we use semi-log paper and we plot the frequency using a logarithmic scale, because as we increase our frequency, we look at things as multiples of the frequency. I even did it when I presented, hey, what is my omega equal to, or what if my capacitor value, or I'm sorry, my frequency equals to 1, or 1 over C, or 1 over 10C, and on and on and on. You could see that I was increasing those by a factor of 10, which when you're using a, excuse me, when you're using a log scale, works really well, works really efficient to do that. So using that log scale makes it incredibly easy as you do your Bode plot analysis, not only to add poles and zeros, but just to come up with a base value. So we're going to look at this one here, and let's look at the system. So, excuse me. I have one finite zero and two finite poles. Well, if you remember from root locus, I can calculate magnitude and angle for this one, magnitude and angle for this one, and magnitude and angle for this one, right? Which I'm going to do by recognizing that I'm substituting in my j omega for frequency. But as I mentioned before, I'm not going to have s plus tau or whatever. I'm actually going to have that value over here. And then I'm going to rewrite that so that I have 1 plus s over omega. Each of these are called break frequencies. And again, I'm not exactly sure how you would talk about what a break frequency is, but when we do what we call Bode plot approximations, a break frequency is when we are assuming that we're coming along at a constant value, and then we're going to break either down or up from that fixed value. So a break frequency literally means you're breaking from this nominal value, and you're either going to start going up, I think not going down, go up, or going down in that direction. So those are break frequencies, and it's much easier to show them to have this representation of S divided by this omega term. And again, we'll start to see that when we build these. So here is our values over here. So here is our 1 plus omega, yada, yada, yada. You'll also notice that I have a value of K out over here. And the reason why I have that value of K is, remember, I might have an equation S plus 2, S plus 3 times S plus 4. I want it to look like this, 1 over S plus something. So if I factor out a 2 over here, right? So I go 1 plus S over a half, I'm going to have to factor out a 2 over here. And if I do the same thing in the denominator, 1 plus S over 3, I need a 3 here, and 1 plus S over 4, I need a 4 over here to make that work. So what I'm doing with this value of K is I'm moving it out front. Oops, not equals, multiply 1 plus S over 2, 1 plus S over 3, 1 plus S over 4. And this term way out front, this 2 over 12 or 1/16 or 1/6, this is our general scale factor. And what the scale factor does is it moves the system up or down, the entire system, the entire Bodie plot, it moves it up or down by a scale to make that value work. And so that's why we have a K term over here. And you will note that K is purely a real term. There are no complex numbers with it. There may be a case when you actually have a pole or 0 at S equals 0, which gives you a phase shift, but that doesn't actually help or doesn't actually influence the scale factor. It only introduces that value. Okay, so let's continue on. So let's add this part over here. So if I wanted to calculate the magnitude of this, I have 1 plus omega over omega sub 3, or omega, yes, sub 3 squared, divided by, and that has an angle. So that's omega over omega 3. And then this one is the square root of 1 plus omega over omega sub 1. That's squared at an angle of omega over, or inverse tan, sorry, being inverse tan of omega over omega 3. This is inverse tan of omega over omega 1. And then the last one we have is the square root 1 plus omega over omega sub 2 squared. And its angle is the inverse tan of omega over omega sub 2. Now, this is where it gets to be the huge advantage of doing Bodie plots. Because if I wanted to calculate the magnitude of that, I've got a bunch of square root terms to calculate, right? So I've got to multiply. Well, I have one term in the numerator, and then I just divide those two terms in the denominator. So that's a fair amount of work. It's not a tremendous amount of work, but it's a fair amount of work. So if there's a better way to do this, where I don't actually have to multiply and divide, then maybe that's the way that I can take it. And so if you recall from logarithms, if you take the logarithm of something, so if I do the logarithm of, let's see, of 10 squared, what do you get? What is a logarithm of 10 squared? Log base 10. It's equal to 2, right? So if I take the log of 10 squared divided by 10 to the third, I can break that term up and I can end up equaling 2 minus 3. Or if I did the log of 10 squared times 10 cubed, that's 2 plus 3. And so the reason why you do logarithms is instead of having to divide or multiply as shown, I subtract or add. And so why do we do logarithms here? It's because instead of having to divide or add numbers here, or multiply or divide numbers, we can just add or subtract. So as we add poles and zeros, if we add a pole here, we're going to add that to the logarithm. If we're going to divide by or add a pole in here, then we just need to subtract. And we normally use the 20, we could use the log 10, but we use the 20 log 10 because it's based on the concept of a decibel, which is a power calculation. And so we just use decibels, and it's based on looking at voltages, but we typically use the 20 log 10 for power conversion. It just makes it easier because our break frequencies are usually called our half power frequencies, and we would go ahead and do that. So instead of using just the log base 10, we do 20 log 10, and then we get our results. So to do this whole expression, instead of having to divide this crazy magnitude number, I can just take 20 log 10 of k, whatever that is. Then I do 20 log 10 of the first magnitude calculation. Then because I've got two poles, I have to subtract those two. So I'm subtracting 20 log 10 of that pole at omega sub 1. And then finally, my last one is subtracting 20 log 10 of that second pole at omega sub 2. Now, I said this is going to save us some work. Does it look like it's saving us work? Doesn't it appear that just doing magnitude calculations here, doesn't that look like that would be easier just to do that instead of doing this whole calculation here? What do you think? Any opinions? Any thoughts? Come on, I know somebody knows the answer to this question or has an opinion. Nobody? Well, I will agree with you to a certain extent. It would be easier to do this equation here for one frequency. But remember what a Bode plot is. A Bode plot is a plot of magnitude as your frequency is varied. So you'd have to do this calculation perhaps a million times. And so doing this calculation, I have to do it every time. But if I can make a couple approximations about this one, I only have to do this one calculation here. And then these other ones I can approximate based on their break frequencies as contributing or subtracting gain from my circuit based on where I am. So what I'll say is this one is only going to contribute positive gain if my frequency is at least omega sub 3 or greater. This one is only going to subtract frequency or gain, I'm sorry, when the frequency is at omega sub 1 or greater. And similarly with the last one, it goes ahead and does that. So what we're doing when we do these approximations is we actually have individual plots. This is a plot for a scale factor. This is the plot for this term running along perfectly fine until we get omega sub 3. This is the plot of this one running along perfectly flat until I get to omega sub 1. And lastly, this is the plot running perfectly along until we hit omega sub 2. And graphically, I have these represented. And that's what we do when we do what are called Bode plot approximations, is just by looking at these break frequencies. We don't have to do any calculations. We can just approximate them using our straight line approximations. And we can add this, plus this, plus this, plus this. And then you literally just draw them together to go ahead and build your Bode diagram. So that's why we use the 20 dB, because if we did this over here, we'd have to calculate it. And what MATLAB did right here, MATLAB did the calculation for us. So what it does is it just plots, what it's doing is it's running at a specific frequency. Let's say it's at 0 hertz, does the calculation, and then moves on to the next frequency. And so MATLAB is doing, however, hundreds of thousands of calculations to do this one, where over here, when I do my bottom one, I can see that these are just done graphically. I'm literally drawing those by hand on semi-logarithmic paper to go ahead and do that. All right, so we'll just look at one term and then we'll really see the power of doing this. So we're going to look at any frequency, and it doesn't matter, or I'm sorry, any term in our Bode our block diagram, and we're going to be using the open loop one. We'll look at that in a few minutes if we have time. So this is a pole or a 0, and so we have it. It's set up, and this is our standard form. So we'll call this Bode standard form, where we have the 1 over S plus divided by omega sub I. And we're going to look at a range of frequencies and see how the system changes. So now we substitute in j omega for our S term, and now we're ready to start actually doing some calculations. So our dB calculation is 20 log 10 of the magnitude, right? So the magnitude of 1 plus j times omega over omega sub I, which is equal to 20 log 10 of 1 plus omega squared divided by omega sub I squared. I think I may have forgotten the square root terms here. Oh no, I did have a square terms. I just included it all there. So yes, I'm good. That was consistent. So now I have my individual term where I have this value over here. So let's look at what happens at low frequencies. So at low frequency, which means omega is much, much less than omega sub I, what can we say about the square root of 1 plus omega squared over omega sub I squared? Well, let's write it. It may be a little bit easier. Let's do it this way. What happens when omega is much, much less than omega sub I? What happens to the omega over omega sub I term squared? Remember, this is fixed. This is a fixed number. So omega sub I is any specific frequency, whereas omega is varying the frequency. So what happens when omega is much, much less than omega sub I? What do you get? Not sure? Let's do a table. Here's omega. Here is what omega divided by omega sub I is equal to. Here's omega divided by omega sub I equal to squared. And then lastly, we're going to look at what does 1 plus omega over omega sub I squared equal. All right, so let's start out with it being much, much less. Let's say it's 1/10 omega sub I. So what we have is omega divided by omega sub I is 0.1. What's 0.1 squared equal to? .01, right? And what is the square root of 1 plus 0.01 equal to? How about 1? Close enough to 1, right? Or approximately 1. Now let's go to it being equal to omega sub I. This is 1. This is 1. And then this becomes the square root of 2, correct? Now let's go omega sub I equal, so this is equal to 10. So this is 10. So this becomes 10 squared, which is 100. And 1 plus 100, wouldn't you say that that's close enough to being equal to 10 square rooted, approximately? So you see, when I'm much, much less than omega sub I can approximate this as being equal to 1. When I'm much, much greater than I can say that this equals approximately 10. So when I do my 20 log 10 of 1, I get 0. When I do my 20 log 10 of the square root of 2, I get 3. When I do 20 log 10 of 10, I get, let's see, that's 20. So remember the curves I did on the previous page when I said nothing happens until you hit the break frequency? Well, if I look at this and I draw a picture here, so this is my plot, at frequencies much, much less than the break frequency, so we'll call this omega sub I, and here's my axis, nothing's happening. So let's change the color here. So hopefully you can see it. So for frequencies at, actually, let me just put this on real quick. So 0.1 omega sub I and 10 omega sub I. This is 0 basically, or it's approximately equal to 0. And then once I get between 0.1 and omega, the worst case that I get is 3 dB. And then once I get to this 10i, it looks like it's just going to be equal to taking 20 log 10 of whatever that frequency is. So what ends up happening is I'm going to assume that this is a pole and it ramps down like this. Oops. Let's try to draw it a little bit. It kind of does one of these and then it kind of peels off from there. So this is the exact Bode plot. This is when we did the actual calculations. We can see 0, 3, 20. We did the actual calculations. It's not, perfect, but it's close enough. If the approximation approach is, I'm going to assume that this is flat all the way until it hits the break frequency. And then at that point, it breaks away at a straight line. And the slope of this line is 20 dB. A slope has a rise over run, correct? So it goes down at 20 dB. That's the rise, right? Negative 20 dB. Does anybody know what the run is? Any musicians in the audience? If you notice, I'm multiplying everything by a value, a factor of 10. So I have 0.1, omega, and then 10. So 0.1, 1, and 10. So what I'm doing is I'm multiplying the frequency by a factor of 10 each time. 0.1 to 1 is a factor of 10. 1 to 10 is a factor of 10, and on and on and on. So the frequency that I have here, or the slope that I have here, it's going down at 20 dB per decade. A decade, that might be a new term, is equal to multiplying your frequency by 10. So a frequency that is multiplied by 10 is a decade above. So 10 hertz is 1 decade above 1 hertz. 20 hertz is not 1 decade above because you've only doubled the frequency, right? So to go from 1 to 10, I multiplied that by 10. That's 1 decade. If I go to 20, that is not multiplying by 10. That is multiplying by 2. If I go to 100, that is multiplying by 10. That is 1 decade. What is a doubling of frequency going to be equal to? Anybody guess or no? Come on, there's a musician in the audience someplace. Anybody here play a musical instrument? I don't. Can I pick on Drew? Drew, you look like somebody who would play a musical instrument. Do you have any musical ability?
I do have musical ability, but I'm really not sure in this
Okay.
case.
When you play, what instrument do you play, if you don't mind my asking?
Bass and guitar mostly.
Bass and guitar. Okay. So what is the A chord? What's the frequency for A chord? Or is that too abstract of a comment?
Like what number
What
frequency
frequency is it, right?
A
When
note?
you strum A, right, it's a specific frequency, correct?
Yeah, I'm not sure though.
Okay. Yeah, so if you could read music, and I don't know about this because my son kind of knows how to read music, is when you read music, there's chords that you have to memorize and positions and all that stuff, but there's also bars. I mean, I don't know how to read music, but the concept is it's all based on frequencies. It's all based on numbers. And when you double the frequency, you're not getting a decade above, you are getting an octave above. Anybody heard that term? So if you look
Yeah, that
at,
makes sense.
yeah, if you look at music theory and you type in one octave is an interval between one musical pitch or another with double or half its frequency. So for example, if one note has a frequency of 440, the note an octave above is 880. The one below is 220 hertz. So maybe unbeknownst to you all, but music theory or music concepts, it's all here, right? When you do octaves, you can actually see that here where it's a doubling of frequency. If I go 1 decade, oh, of course. Let's see if this helps. Music theory, I don't know, we'll see. No, of course. It's always gonna be this, but. Let's see if there's something here, great. If not, we're gonna punt on it really quickly. Okay. We'll try it this way. So teach me audio. Let's try that. Let's see if there's an octave or decade keyboard. Let's see if we can find one. We could play it even. Should have done this previously. I apologize. I was just looking for let's try MIDI and see if we can actually play it. Last one, and then I'll give up. Just sometimes like playing music, so. Virtual piano. Let's see if we can figure this out. I don't want to be world ranked, that's for sure. All right. Well, maybe it doesn't show it this way, but you can hear, right? So let's see. Let's pick a key. Let's pick F3. Actually, you know what? Let's try this. See if we can find it this way. If it would say the frequencies, we could actually play it, but I don't know if there's one that actually shows the frequencies. Ah, my finger's not working today. Let's see if this one works. Great. Okay, so name of piano keys, that's great. What are the frequencies? No, okay, well, I'll punt because I can't figure it out, but you can see all the keys, the different names. I would have thought we could have found one that generates a specific frequency, but you know, this A key or A2, it's just a specific frequency. That's all that is. So I'm gonna punt on that because I can't find what I want. So we already talked about this break frequency, and we have a 3 dB. When we double the amplitude, we double the power. So, whoops. So the thing about the powering is, and we call it the half power frequency, is when we're down 3 dB, that is technically considered our half power frequency. Why is it half power? Because if you remember under this expression, it's 1 over 1 squared. And when you do the 20 log 10, you're going to get exactly half the power of the output. So at the break frequency, you're half power away from what the actual power of the system could be. So here's that calculation we did. At 20 log 10, we're much, much less than omega sub 1. So you can see I did my omega. We're going to say it's approximately equal to 0. At the break frequency, we have 3 dB we calculated. And over here, we're going to just allow that to be some value of omega. And that just equals to 20 times whatever power that raises. So you can see that our frequency our 20 log 10 is just going to be approximating by just taking 20 log 10 of omega, whatever that value is. So that's where we get the 20 dB per decade. And so our approximation is here. So no contribution whatsoever. And then once we get to the break frequency, we go, in this case, it's a 0 because we go up by 20 dB per decade. But if we went in the negative direction, it'd have to be a pole, so we go down. So hopefully, and I will pause here for a moment, this here is how you were taught to approximate a Bode plot. And you can see the dashed blue line, this is the approximate. And the worst case error between the approximate and the exact happens at the break frequency. And the worst case is going to be 3 dB. That's the 3 dB difference between the two. So if you're exact and you're using Bode plot analysis, you're fine. You don't have to worry about it. But if you're using an approximation and you want to get, pretty accurate results, what that tells you is you want to be well away from your break frequency so that if you're relying on it to be giving you really good results at those frequencies, then what you have to say is, I need to stay well away from that. So perhaps if you've gone through and you looked at it, you would actually do a high pass filter or a low pass filter, and you say, this works for a break frequency at, let's say it's 500 kilohertz, but I'm going to be well away from 500 kilohertz to have it either amplify or attenuate the signal. So that way I don't have any frequencies that are passing through that I don't want it to. So that's why if it's a 500 kilohertz break frequency, you probably wouldn't operate it for systems that's going to have more than 50 kilohertz or something like that, because you're going to have too much goofiness in your output to get real results. Okay, so pausing here, is this how you were taught break frequencies and Bode plot analysis? Anybody? Did you do Bode plot approximations like this, or did you not do Bode plots when you did frequency response? Can't remember, or just feeling that this is the last week of the semester?
I don't remember it. We may have and I may have forgot it, but I don't
Okay.
remember doing Bode plots before.
Okay. All right, thank you. Yeah, but this is how you actually, the math behind it. We do everything in semi-log, and you can see this is semi-log paper because look, this is 1/10. And the spacing between 1/10 and 1 is exactly the same as the spacing between 1 and 10. So this is on a logarithmic axis. But over here, the difference between 40 and 20 is exactly the same as between 20 and 0. So that's why we would call this semi-logarithmic paper. And that's how you do the calculations for doing attenuation or doing magnitude plots. Okay, so here's a 3 dB, et cetera, et cetera. So here's a more detailed one. Again, doing it with MATLAB, you can see, the plot where we have a break frequency and it's all relative. So this is a relative plot. So log 10 omega of omega sub 1. So the reason why this works at 0 is because they're the same. So remember, log 10 of 1 is going to be equal to 0. Why? Because 10 to the 0 equals 1. So basically, when you do the logarithm of something, you're pulling out this number over here. So log 10, log of 10 to the 0 is equal to 0. So it's whatever power 10 is raised to, that calculates that. So that's why if I have 10 cubed, that we know is 1,000, right? So that's equal to 1,000. But if I take the log of 10 cubed, that's equal to 3. And the reason why we use log again is because it can make the math really easy. And so if, for those of you, we talked a little bit about this class, if you had a slide rule, the way that you could multiply really big numbers, let's say you had, I don't know, 10 to the 5th times 20 to the 7th, essentially. So what you would do is you would say, oh, well, that's a big number. That's hard. So what I'm going to do is I'm going to break it up. I'm going to break it up to 10 to the 5th times 10 to the 7th times 2. And then I'm just going to go log of 10 to the 5th And this is because I'm doing exponents. Now I'm multiplying becomes addition, log of 10 to the 7th plus the log of 2. And so that's going to be equal to 5 plus 7. Anybody know what the log of 2 is equal to? I don't know. Let's just say it's equal to 0.2. Let's approximate it. So this is going to be equal to 12.2. And then to find out what the final answer is, you go 10 to the 12.2 is what your final answer is to be. So that's how you can multiply really big numbers by just using logarithms, because you're just adding and subtracting. Okay. All right, so last little bit, because we're getting close to running out of time. I think I have 9:05. So what's the frequency response for a constant? So if I look here, I have, I just take 20 log 10 of k, and then that has 0 degree phase shift. So here's my magnitude, and it's going to be equal to 20 log 10. So here's my value of k. K is greater than 1, and my phase shift is here. If k is less than 1, then we know we take the log of a positive number that's less than 1, we're going to be negative down here. So that's why we end up over here. But the phase shift is not changing at all. In a real number, no matter how much you change the frequency, the phase shift is not changed. Okay? So here's the positive constants. You can see it's positive or negative. This is the case of g equal to 4. And the blue is the case of g equal to a quarter. So 0.25, not negative. You can't do logarithms to get negative numbers. But for positive numbers, you can do it, even very small numbers. But you can see I've got two magnitudes here. Positive, what is that, 12 or so? Negative 12, but the phase shift is always going to be equal to 0. So here's a pole or 0 at the origin. So what we see for a pole or 0 at the origin, we have an S or a 1 over S. Well, what we do is when we substitute in j omega over here, what we see is that there is our magnitude of omega at an angle of 90 degrees. So we take 20 log 10 of 90, 20 log 10 of omega, and what we see is that immediately we start introducing a positive magnitude here. And where it starts to do positive is at 1, right? Anything below 1, it's going to be a negative dB per decade, but anything that is positive, it starts at 0 and then goes up. And then we look at the phase. Well, we can see it's just e to the j90. It's always going to be positive 90 degrees. Now we do the case for a 0. And if we think about a 0, the 0 is going to be contributing because we're subtracting the log. That's going to be going down at 20 dB per decade. And again, it crosses the 0 axis at 1 radian per second, essentially. Not 1 hertz, but 1 radians per second. And if I look over here for the phase shift, no matter what, it's always going to be minus 90 degrees. So I have a minus 90 degree phase shift. So if I have a pole or a 0 at s equals 0, then I start contributing either positive or negatively to the gain. And that just goes where you're going to plot. So you can plot these all the way back. Sometimes you go with really small numbers because you're trying to show your break frequencies and your plots correctly. So sometimes you have to start a couple of decades below the 10 to the 0. So you just have to make sure that you have those values here. But the phase shift is always going to be plus or minus 90 degrees. So whoops, this is touching. And then sorry, it's really sensitive. I don't know why it's so sensitive. And that's what we have for a plot over here. You can again use MATLAB to plot it. So if we have a non-zero pole or 0, we're going to go and start plotting immediately at 0 until we get to the break frequency, and then we're going to approximate it in this direction. If it's a pole, then we go down at that value. Oops, what's going on over here? Sorry, there's some chicken scratches from previously. What's going on? So we'll end with this slide because I'm kind of going to introduce it really quickly. So let me go ahead and duplicate this. So the thing about, can you see my screen still?
Yep.
Okay, so what we see is for polar zero, non-zero polar zero. So before we talked about a scale factor has no phase shift. If it's a polar zero at s equal to 0, we have either a plus or a minus 90-degree phase shift. Over here, we do the same approach, but remember, we're using the concept of an inverse tangent. And an inverse tangent of 1 is 45 degrees. So what we do is when we do our break frequencies, we go 1/10 of a frequency before. We'll say that's equal to 0. And 1/10 of a frequency after our break frequency, and we approximate it with 90 degrees. Because when we do the square root of 1 plus 1, which is 2, that's 3 dB off. But over here, it's a huge difference. It's 45 degrees. So the difference that we do for for phase plots is we say that it starts to contribute at 1/10 the break frequency. So here's our break frequency, omega sub 1, omega sub I. So if it's a 0, it contributes a positive 45 degrees per decade. And it starts at 1/10 the break frequency and ends at 10 times the break frequency. And if it's a pole, then we go down at 45 degrees per decade. So remember, the direction of going up or down just depends if it's a pole or 0, but the 45 degrees doesn't change. So you can see this one, the error is a little more significant because you can see at 1/10 we get 6 degrees, but we'll approximate that as being equal to 0. And then at 10 times the break frequency, we're off by that value of 6. But to simplify things, the industry folks or industry standards said, you know what, let's just go ahead and let's just use this approximation. So this is how you calculate the gains, the amplitudes, and the gains, we've calculated those in the past. But that's essentially, all that I wanted to do for, just give me 1 minute, bud, okay? That's all we needed to do for this one. So the timing is almost perfect. I'm just about out of slides. You can take a look at the example and you can see how I have a scale factor. I have 1 0 and 1 pole. This break frequency is 3 hertz. This break frequency is 12. This is 50. So we have a pole at s equals 0. So this is contributing constantly plus or minus 20 dB per decade. And because I'm starting at 10 to the minus second, I have to go up 40 dB per decade. That's this red. The scale factor is going to be a constant 20 log 10 of 1,000 divided by 3, or 1,000 times 3 divided by 12 times 50. Just 1 more minute, okay? And then I take that, and I've got this green line, and then I have these other lines, and that's my plot here. This black line. And then I do my angles. So I have 0 and on and on and on. And that's my final value. And this is the example. So I apologize. Just 1 minute, please. So I'm out of time because I have a kid banging on the door. And again, I apologize, but we're pretty much out of time for the class. Any questions on anything? All right, so you can take a look in the course folder, but on Thursday, I have the review for the final, so we'll do that on Thursday. So have a great day, everyone, and I will hopefully see you in person tomorrow. Take care, everyone.